Hello, and thank you for joining us for ArcelorMittal's webinar with Automotive Manufacturing Solutions. I'm Nick Holt, an editor of AMS. Today, I'm joined by Mathieu Ambelard and Jerome Favreau from ArcelorMittal's Global R&D team. In this webinar, Mathieu and Jerome will explore why e-mobility needs smart steel. So this presentation will cover the construction of battery packs, chassis and body in white in relation to electrified vehicles and the company's S-in-Motion projects and developments. Before we start, I'd like to invite all of you to send questions in to Mathieu and Jerome. We'll pick these up in the Q&A session at the end of the presentation. Just type the questions into the box in the lower right hand side of your screen. Also, if you experience any technical issues during the session, please let us know using the Q&A box and our team here will try and fix it. We hope you'll find this webinar stimulating and informative. And with that, Matt, I'll hand over to Jerome to start the presentation.
Okay, hello everyone. Thank you, Nick, for the introductions. And thank you to everyone for joining this webinar. So, as already introduced, we will speak about our project for electrification and more especially our S-in-Motion BEV solution for battery pack. So first of all, I don't know if you're aware what S-in-Motion is. S-in-Motion is in fact the generic project from ArcelorMittal to build a catalog of solutions by taking into account of crash load costs, technical and also cost constraints of the automotive car makers, with of course the idea to have solutions ready for implementations. So okay, so just waiting. Okay, so the next slide is there. So regarding the content, first of all, I will give you a couple of words about the context of the BEV market, even if I think that you are well aware about that, and also explain the approach and the objectives of the project. After this first point, my colleague Mathieu will explain you the main technical parameters influencing the battery pack, and after that go deeper and explain you our S-in-Motion steel battery pack concept. And at the end, I will bring some additional elements such as further projects we are running on the electrification, and also a couple of words about our electrical steel solution, which is also, of course, part of the electrification. So first slide, is, let's say, the possible support can bring ArcelorMittal to the OEM or the tier ones within a car development. So basically, more or less 6 years prior to SOP, a kind of pre-development is already starting at the OEM or tier ones. And here, basically, ArcelorMittal is able, thanks to the S-in-Motion product catalog, to bring the idea and the generic steel solutions which can be already introduced at the customer and integrated on the model of the customer. Once the pre-design is already advanced, ArcelorMittal can also here start co-engineering with the customer with the idea to see how to optimize the use of steel in order to reach the best crash performance of the customer car manufacturer car. And of course, after 2-3 years prior to SOP, we can of course continue to support with EVI and processing support such as stamping, joining, support in press shop or by numerical approach. So it was just a short introduction to show you that ArcelorMittal can support the customers from the early design phase of the vehicle up to the start of production and even after with the quality management. So now back to battery electric vehicles. So today, even if you probably don't see still already a lot of battery electric vehicle on the street, this market is going to increase in the coming years. And based on the last IHS data, we already foresee more than 10% of battery electric vehicles in China or in Europe, which represent in Europe around 2.5 million vehicles. So, of course, we can now imagine that the scale-up will put more pressure on the cost constraint due to the high volumes of productions. So this is why we decided to work also more intensively on the electrification in order to bring also the solution for mass production for the electrification to our customers. Regarding the context, today, one of the key points, of course, of the battery pack is the battery cell and the battery trends themselves. So today we are, let's say, in a very increasingly fast development of the technologies, and even if we are waiting for the solid state battery in a couple of years, but probably not before 5 to 10 years, we have today a very, very dynamic market. For sure, lithium ion are today a kind of a mainstream solution, but with also diverse geometries and also diverse chemical behavior. And of course, the cell package vary a lot with different energy density, mechanical resistance, fire behavior, all different technical points we have, of course, to take into account by designing our solution. So now, if we look at the integration of battery on an electric vehicle, we can have two solutions. The first one would be to use an ICE structure design and add the battery on, let's say, empty space. The second one would be to redesign the vehicle and adapt it to have a larger battery pack. And based on study we can see that today, in order to achieve a larger range, which is the main objective today of electric vehicle, we need to have a dedicated battery pack. Without this battery pack, we would have a too limited energy range. And this is why we started our projects in order to help the car makers to meet their goal for the electrification, with the idea to demonstrate how the ArcelorMittal advanced high-strength steel solution can help the customer to meet their goals for battery pack structure with regard to key elements, which are the performance, the mass, the cost, and the modularity of the solution.
Okay. Good afternoon, everybody. Now we'll go on with more technical details from the project we ran for the last few months. First of all, okay, we are not car makers. We, however, tried to take into account all the main constraints that OEM have to respect. In this slide, you can see that many parameters are influencing the battery pack design and the choice towards the material and the thickness of the material. At the vehicle range, of course, the range objective of the OEM will fix the volume of the cells and the mass of the cell the battery pack has to take inside. At the module level, there are also a lot of major parameters like the cooling technology, the charging time, and so on, the strategy regarding repairing, recycling, and so on. And also at the component level, many parameters have to be taken into account. So, of course, as ArcelorMittal steel supplier, we are not able to decide all of these parameters. This is the job of the OEM. But for this project, we try to keep as generic as possible and to fix also rather severe load cases, severe condition, to see how steel can bring value to this module. So on the right-hand side, you have some of the most important aspects we have to take into account from a mechanical point of view, but also other point of view like tightness, fire resistance, and so on. The one in dark gray, we will show some result later in this presentation. So regarding these parameters, you can see in this slide the parameters that we've been using for this project. So as Jérôme said, we used our S-in motion generic C-segment model to begin with the size of the battery pack. So we begin with 270 liter of battery pack outside the volumes, and on the basis of data given by our partner Ricardo UK, we used the generic data like density of energy, ending with 140 liters dedicated for the modules, represented 320 kilo of batteries, representing also 60 kilowatt hour and about 450 kilometer range. We have decided to use a cooling system that is made today of steel, and you will see that not everything is fixed yet on this thermal analysis. I will explain later on. And we also have decided to use 18 fixing points all around the battery pack. There's no fixing point in the middle of the pack. You have here a top view of the battery pack on the C-segment vehicle, and it's the blue attachment point outside the battery pack. I show you directly how one of the alternative battery pack have been designed as an exploded view. Is positioned normally regarding the Z-axis in with on the top cover as number one, very light, and on which, because in our case we managed not to have welding on this part, we would like to promote our high performance corrosion coating by avoiding e-coating, so to reduce cost as well. The number 2 to 6, they are welded, so we use e-coating corrosion protection on top of Jetgal coating or GI coatings. So it's made of 3 main structural areas. So the number 2 is the internal cross members. The number 4 is the frame all around the pack, and at the bottom, the number 6 is the shield and its reinforcements. So we found that number 2 was mainly dedicated to, of course, stiffness, first frequency of modal analysis, resistance in drop conditions, shocks, and also on crush resistance, but less on crush resistance. So on these cross members, we have we propose to use Martinsite steel 1500, very high yield strength material. The same for the frame. The frame is more dedicated for crush resistance from side pole tests, for example. And also we will show how we manage to reduce the weight using high strength Martinsite 1500, and to finish the lower shield that is here to resist to intrusion from below when you are rolling over an object, and that this object is knocking the bottom side of the battery pack.
Okay, so as you understood, Martinsite 1500 is one of the key points and the key steel of our solution. So basically, what is this steel? This is a full martensitic steel dedicated to roll forming and crush forming applications with a very high yield strength from 1200 megapascal and a UTs of 1500 megapascal. Regarding the design, it allows also to have a very small radius, so which makes that it's a perfect steel for a battery pack. And to give you an example, we can bend radius as small as 4 times the thickness. So we deliver this steel, of course, with very good flatness in order to achieve robust geometrical tolerances, and also the mechanical properties are also extremely stable along the coils. Today, we can deliver this steel from Europe, from North America, from South America and China. Today, we are not ready for commercial delivery, but possible development possibilities are opened, and in Europe we can also deliver the steel with Jetgal. Jetgal, in fact, is technically for the customer and the properties equivalent to an electro-galvanized, but present different advantages, which can be further discussed, let's say, in separate discussion. Regarding the coating, we can also, as I mentioned, electro-galvanized, Jetgal, and also bare. And regarding the gauges, we can deliver for 0.8 to 2.0 millimeters, which covers all the needs. And on the request, we can go down to 0.6 millimeters.
Okay. So now we will present you the different performances of the pack under different load cases. I will begin by crash resistance. So several tests exist in different normative documents. We have selected the China GBT last version condition. So it has to respect 100 kilonewton resistance from a pole of 150 millimeter diameter. We have selected to use finite element analysis specific criteria to adapt to this test criteria. In our case, we have a very small gap between the internal side of the structure and the module in order to increase at maximum the volume of the cells and the range at the end. So you have only a 10 millimeter gap between the internal side and the modules. Okay. And the second criteria that we have selected in order to be very safe is to have no contact between the structure and the module during this test. We have been working with partners that are checking, for example, fire resistance in all kind of conditions, and it's their advice not to touch the cells inside the pack. So that's what we have done in our calculation, and you are here the results of our pack. So you have une vue en coupe, a cross section, sorry, of the battery pack. In blue the cell and the 10 millimeter gap from the frame, and you can see that on the graph that we reach 100 kilonewton resistance force before the internal wall is touching the cells. We would like to mention that for this test, the frame is the main structure involved. The yield strength of the material of the frame is very important, and it has to be maximized. That's why we have selected Martinsite 1500. And you can see in the right graph that if you use a lower grade, so 700 MPa, for example, you lose 14% mass, or you increase the weight of 14%. So this is important to Martinsite 1500 is important to keep weight of the frame as low as possible. The second load case is intrusion from below. So in this, for this condition, there's no normative test yet. The state of the art is not stabilized yet. We can find bollard test or misplaced jack tests where you misplace your jack and you push on half of the gross vehicle weight on an impactor of 50 millimeters. These were not found to be so the most damaging condition. We have studied data of a real accident case condition, and we have selected this in our study. So it represents an impactor of 20 millimeter diameter, so a small object, and you have to respect a load of 35 kilonewton without fire at the end. That's why we also have taken into account in our condition no contact between the structure and the pack and the modules. Sorry, the cells. So in this slide, you can see how behave the shield, and that is the main structure involved in this load case. Again, the yield strength of the material is very important, and is again more important than the previous case. The second one we found that was very important. It's to have a flat, completely flat shield. So it's not so obvious to have a flat part in automotive, but in this case, if you want to take the best from the yield strength of your material, you have not to you have to be directly to push on your material, and so to be very flat. In this case, you can see that reducing the yield strength from Martinsite 1500 to 700 MPa, then you lose 30% weight. So it's again more important to use Martinsite 1500. In this case, we reached the target with a thickness of 1.35 millimeter. Regarding drop tests that you can also find in different norms, we have selected the Korean norm, that is the most severe one. So you imagine to have a 430 kilogram module with the cells falling from about 5 meters high with an angle of 15 degrees. And in this case, we don't want a rupture of the structure. And in this case, we found that the cross members were the most important. We found that the longitudinal cross member, for example, could bend very hard if you have not a sufficient high yield. And while the cross member is bending, the risk is to touch the cell on each side of this area. So we also use this same grade, Martinsite 1500, to avoid a hard buckling. However, in this case, it's so difficult that we did not succeed not to touch the cell. What we wanted to avoid is very hard contact with the cells, and you can see in the picture here that you touch the side of the cell. You cannot avoid, or we did not succeed to avoid this to happen. Again, you can see that the yield strength of this cross member is important. We found also that the lower cross member were important, and that you can manage to have more flexible part to reduce the energy going into the cells. Shock tests. So you have also several types of shock tests. Proof shock, where you don't want to deform the structure, or abuse tests, where you don't want to have a rupture. In our cases, we have tested all this, and we show you only the more difficult one is the 25G vertical acceleration on the 320 kilogram of cells in the middle of the pack. And we succeed to have low strains in this case. So this is not the most difficult test to pass. But for the proof test, where you don't want deformation, you also need to stay in the elastic range. So you need a high yield strength of this material. Regarding modal analysis. So Ricardo, our partner, gave us a good way of working by respecting at least 35 Hertz as a first mode. So I remind you that there's no attachment point to the body in white in the middle of the pack. You only, in our case, we have decided to fix the pack only with the blue part you see around the frame. This is very important. With our design, we reached 37 Hertz, so it's quite good. Of course, in this case, the material except thickness is not playing a role. And last, probably not the least in terms of development, it's a vibrational performance. We have used ISO norm to run, I would say, first analysis regarding vibrational. Okay, it's just to say if we find problem at this stage by calculation, you stop your project or you improve your project. If you're good, you will have, when you will do some prototypes, you will have to check the assembly, the welds, and so on. Of course, in our case, we were quite far away from the critical area, so we think that it's not too bad. Okay, so these are the mechanical performance of part of the work. You can see that we have selected rather severe load cases, and of course we have to adapt to each customer specifications. It's a bit the same for corrosion resistance. We have a panel of products regarding coating that can answer the need of everybody. We hope so. Between the Zanielist Protect with the thick layers that are able to cope with the corrosion without e-coating, in case you don't have welded parts. So this is the case for the top cover. Regarding the other parts, of course, they are welded, they are assembled, so you need e-coating, but you can deal with either Jetgal, uncoated, or GI, depend on your needs and your acceptation regarding your cases. So we end up with weight. Okay, as I said at the beginning, this weight is not going from nowhere. Of course, it depends a lot of many parameters, as I mentioned. So you will find here the bill of material with the weight of the different parts. Again, if you have more weight of cell or less weight of cell, this weight of steel, this 77 kilo, will evolve. And we as Jérôme said at the beginning, we are able to take into account your specific constraint and to adapt to find the best solution at the best weight. We position our concept versus the benchmark. So the source numbers, the number source, sorry, is A2 Mach 1, where you can find the overall battery weight and the kilowatt hour of the different vehicles. So you see the trend. So I mentioned that, of course, in this weight, there's cells and so on. They're all equipment in there. So the weight of the steel pack is a small part of this number, but you can see that with our hypothesis, we are not too badly positioned. We are well positioned, and this line is a trend made of either aluminum pack or hybrid steel and aluminum pack. While in our case, we are full steel, so it's not too bad, and this is thanks to the use of Martinsite 1500, of course. Okay, we have used in also aside the project different alternatives, because some of you request a tray or higher stiffness or different solution. We also see from the benchmark different solutions. So we try to understand the differences between all these alternatives. And you can find in this graph, in this slide, the different advantages we found and disadvantages we found using a tray. For example, yeah, we can expect that the tightness management may be easier with a tray. We found, however, assembly sequence a bit more complicated and a bit less volume available for the cell. That is the same for if you want to increase the stiffness by using two longitudinal cross members, because of course two cross member means less volume for the cells, but you increase the stiffness of the pack. And last point, if you add, of course, fixing point of the battery to the body in white in the middle of the pack, as it is done at some OEM, the 37 Hertz that we found is directly switched to 60 Hertz. So the frequency you want to reach, of course, depends on the boundary condition you use in your project. Okay. We also mentioned in this concept modular approach for cost optimization. It was a choice from the beginning to use roll form sections that are well adapted for Martinsite 1500 as well. You have a straight shape parts that are cost attractive and with a very high degree of material utilization. It can be adapted in terms of length, so on overall size of the battery pack. There are only the big part that are slightly stamped with also a very high degree of utilization, and the top covers, the cooling system that was done in using cladded panels, and of course the lower shield that is not stamped at all. As I mentioned, it should be flat. We found this at least that it's better to be flat. Of course, we have been working with tier ones to review the forming validation, the assembly validation, and the assembly sequence of this project. Now we know that you don't have all the same use regarding forming and joining, so our teams are able to adapt to your use. Earlier, I was talking about the weight of the battery pack. We very often heard about the pack is lighter or is heavier. As I said, it depends a lot of condition, and I want to highlight it on one case is the intrusion from below. So on the left, you have the condition we have selected from the project, real accidental conditions. You can see that we managed to pass this load case with Martinsite 1500 in 1.35 millimeter. If you don't want to use this condition and you use, for example, a misplaced jack test, so you have the condition we used in also to check this below. You can save straight 8.5 kilos, so about 11% of the battery pack. So, as I said, it depends a lot on the condition you have selected. Cost comparison. Okay, we've been working with an independent company, as we usually do, with special hypothesis, because we all know that the cost depend on the material you have, on the plants you have, and so on. But we are used to work on a kind of greenfield conditions to compare things. Okay, again, this can be adapted to your conditions, but we found a very high advantage for steel versus aluminium of around 80 to 100 euro per vehicle using steel. So it was, of course, one of the objectives of this project.
Okay, so we just finished the presentation of our battery pack concept, and here we just have a couple of slides to show you that we are working further on the electrification. So in fact, of course, the battery pack is one of the key elements, but not the only one. As you understood, the battery pack excuse me, the battery pack adds more than 400 kilograms to the vehicle in mass, so it means that it impacts also the crash performance of the complete body in white and also just the chassis. The chassis is also mainly has also mainly to be adapted because, of course, of the different engine technology. So this is why we wanted to see how steel can meet the challenge of the electrification and the overweight and the weight added to the vehicle. And this is why we have started to work on a project based on the SUV architecture. So up to now, we changed the powertrain, and we started recently to work on the chassis. So we are currently, as I mentioned, investigating the different load crashes, and we are expecting to have results in a couple of months by the end of 2019. And in order to continue the work, of course, we focus on the body in white. So here the work is already started, still ongoing, and we are, of course, dealing with the different challenges of the electrification. For example, the ergonomy. If we put the battery pack under the floor, of course, we have to increase the Z position of the floor, but we have also to find the right limit to have a good ergonomy of the passengers and of the drivers. So here's one example. Another example, which is crucial, is that we have to rethink the pole crash management, because, of course, first of all, we add a lot of weight to the vehicle, and the second major point is we have to protect the cells, as Mathieu mentioned several times. So here we designed a clever architecture, a clever solution combining an architecture and the use of our top advanced high-strength steels, such as Martinsite 1500, but also usable 1500. And thanks to that, we are confident that we reach the different load cases. Of course, we are working also on different parts, such as the B-pillar, such as also the cross members, because of the different architecture due to the battery pack and to the further weight to manage in case of crash. So this study, as I mentioned, is already ongoing, nearly finished, and we will be ready to show you and to present you results already in a couple of months, and of course in a future webinar. So in order to end the technical presentation on the electrification, of course, we had also to say a couple of words about our electrical steels, because it's a major component of the battery electric vehicle. So today we have a wide offer which pass to the different requirements you may have. If you want to have a high motor efficiency, to have a larger range of your vehicle, we developed our iCARe Save and iCARe 420 Save family. So the iCARe 420 is an improved version to still increase the efficiency of the motor. We have also, for high performance motor, we developed also the iCARe Torque to be able to provide a high torque on your electrical engine. And if you are looking for a more compact or lighter motor design, we developed also the iCARe Speed, which is suitable to provide a higher power density. So here is just a short overview about our offer in electrical steel. And for us, it was also important to mention that we have a a large enough product to cover all the needs you have, and you can of course find more information on our automotive.arcelormittal.com website. Okay, so now time to come to the conclusion. So as a point, I think the first point and the most important point is that the fact that advanced high-strength steels are well adapted to protect the cells from the most severe conditions, especially our steel dedicated to wall forming, which is the Martinsite 1500. Based on the estimation done by an external company, it appears that our steel battery pack is from 80 to 100 euros cheaper, excuse me, compared to an equivalent aluminium solution. It's also important to remember, if we speak about weight of the solution, that we have to put that result in front of the load case we took. So we have here to remember that the performance and the solutions which has been presented by Mathieu took today into account the most severe crash and load cases. And as the last point, I want to highlight again that we are ready to adapt to the constraint of your companies, of your design, to bring our deep knowledge of our innovative product for optimal solution to bring you the weight saving and the cost saving you may need. And of course, the steel remains the material of choice for e-mobility solutions. And after this webinar, I'm pretty sure that you are convinced. Thank you very much.
Well, thanks very much, gentlemen. We'll start looking at the questions now, so I hope you're prepared. We have somewhat limited time left. However, any questions, and we do have a lot of questions, generated a lot of interest as I think we thought it would do. Any questions that we don't get the chance to answer or ask today, we've forwarded on to the presenters, and then those guys can get back to you and clarify any things you've got to ask. Excuse me, as we would expect, very technical questions in this field. So I'll just start reading through them. So if you're both ready, first question, Matthias and Jerome, is what is the risk of hydrogen embrittlement of the Jetgal coated Martinsite 1500 due to corrosion in the field, and have you investigated this?
Yes, of course.
Yes, of course, we have investigated this point. So first of all, Jetgal is also a coating which has been developed to optimize the hydrogen embrittlement, to avoid, hydrogen embrittlement by reducing the hydrogen intake during the production at ArcelorMittal plants. But I don't know which more details you may expect, but of course we can be ready later with experts to go deeper on that topic. But yes, we have the solution.
Thank you. A question here regarding, you were talking about the strength of the battery frame. This question, have you been investigating the battery strength or the battery frame strength regarding intrusions from the interior of the vehicle? External crash, I'm assuming. So.
Okay. We can see, yeah, it's right. We don't see it very well on the picture and on the cross section that we showed. There is a resistance from the cross members, internal cross members, but this has not been the most critical point. I did not mention it, but in this condition, in this calculation condition, we have used our state-of-the-art criteria regarding the behavior of the steels with crash rupture. So we have not used a very simple modeling. We have checked that the frame was not damaged, any rupture, any problem of crack, for example. But I don't know if the question can be more precise regarding the condition of shocks from inside. We have considered, I don't know, I imagine that the modules were fixed and the fixation were not damaged. So there's no shock from inside the box to the frame. But we can discuss about this case if you think it's relevant. We can have a look.
Thank you. Yeah, I mean, any of the questions that they want further clarification on, obviously we'll pass on the contact details to the guys at Arcelor, and they'll be available at greater length and time to consider the questions and discuss things further with you if anyone's got any more questions pertinent. Moving on to the next question. Question here: are the Martinsite frame components roll formed, and what size of inside bend radii are possible with this material?
So yes, it's roll formed.
It's roll formed, and it was 4 times the thickness.
Yeah.
4 times the thickness. It's radius achievable.
So now, according to the OEM, some say to succeed 3 times the thickness, some 4. We have selected 4 to be a bit safe regarding the process, but yeah, now it depends also on the tuning of the line and so on. But yeah, it's roll formed.
Yes, and of course, just to be clear, for all our generic solution, we design the car by taking, of course, into account as a possibility of our materials. So everything what you saw here has been validated by the numerical approach, of course, if possible, by prototypes. And of course, as I mentioned, we take into account the material technical capabilities.
Thank you. A question here regarding the joining technologies. What joining technologies are used in the construction of the battery tray? Is it welded, riveted, or adhesive, or a combination?
Okay, this is a combination. This is a good question. The assembly can be a bit tricky, especially with very severe load cases as we have selected. We try to use adapted assembly techniques first, not to have too many thermal distortions, for example. So there's no very big length, long length of mag welding. So there are some in different points. There are also laser welding. We find that it's well adapted to this very long length of assembly. There are a certain number of bolts and screws as well, because of the assembly sequence. For example, it's not so to obtain the performance in a drop. We have to fix the lower part of the battery pack, the shield, to the upper cross members. And when we designed the assembly sequence, we had to find some tricks to make to use some holes in the shield, for example, some small holes in the shield to put some screws, and afterwards to manage the tightness of the whole system by filling the holes. So there are some different assembly techniques. and these were reviewed by tier ones, now, for example, we also left open the assembly technique from the shield to the frame, because some of you want a double access from the top, but also from the bottom to ensure repairing and so on. We can think of different techniques to fix the shield to the frame. We also looked at maybe exotic assembly techniques like mesh welding or roller welding, because it's quite interesting in terms of cost. There's no filling material. There's no not too much distortion. It's quite quick. It's if it's well managed, it's compatible with tightness. So yeah, we are looking at even more exotic assembly techniques. And we have data if we want to go further into detail during a face-to-face discussion.
Thanks. We've got time just for a couple more questions. Question here: in the crush simulation, did you constrain the battery box at any particular fixation point or fixed points?
No, we used the test conditions, so it's like it was put on a table. We took into account the gravity, and that's all. And I showed only one results, but on the norms, we have to check all the more critical areas. So we applied this load all around the pack, even on the brackets, to see how it behaves. I showed you the most severe condition where the length between the cross members and the pole was the longer length. But there's no specific fixing to through, for example, the bracket.
Okay, we have one last question. Time for one last question, and that is, you mentioned fire resistance. What can be expected in terms of steel versus aluminium in this respect?
Okay, so this is one point we are studying with the French Institute in charge of checking the fire behavior of a lot of things, and in particular the automotive and the battery pack. So Ineris is playing with a lot of battery packs and trying to put fire in different conditions. So they have developed knowledge, specific knowledge, to make some models. We are not doing this by our own. We are working with this partner. The study is not finished, but there are already some interesting points. Is that we took into account different power into the batteries. We took into account the different kind of chemistry, and the oxygen into the cells, because some say that it can burn alone with no oxygen from outside. It's not what we found. We found that as long as there's no hole in the structure, as there's no oxygen going from outside to inside, the fire stops by itself. Whatever the initial condition, short circuit or another event. So this is one point. So from the strategy point of view, we see that it can be of much interest not to deform the battery pack even in very severe conditions. That's a bit why we have also selected these conditions. So we do expect that the battery pack is not much deformed at all. The second point, so okay, if you have an accident at 200 km/h, okay, you don't expect that everything is still fixed, huh? Okay. Now we see that we don't have straight conclusion, but in all conditions we can see that temperature can go very high as soon as oxygen is going into the cells, and fire develops. And in any situation we found that still has high interest, because it's not melting, because the melting point is much higher than aluminum. So this should help not to help oxygen to go into the battery pack. This is not the case for aluminum, because you can reach temperature of more than 600, the melting point of aluminum, for a long time. The yield strength in temperature also of steel is a strength from the steel point of view. Now, what we don't know is all these positive aspects of steel will be used in real condition. We don't know yet, but we know that the full point in fire condition is to have few minutes time for the occupant to go away before being injured by fire. We think that it's more probable with steel than aluminum. Now we should, as you probably do, make some prototype with all the equipments and the sealants and so on in it.
Thank you. Well, we'll draw the Q&A session to a close there. We have a few more, well, quite a few more questions, but we'll pass these all on to Mathieu and Jerome to follow up on. And we'd like to say thanks to both for a really informative and very topical webinar. A lot of interest out there. As always, the webinar will be uploaded to the AMS archives and accessible in the future for any colleagues who have been able to join us for the live presentation. And you can access these and our previous webinars at the Automotive Manufacturing Solutions homepage. So thanks to everyone for taking part with us today, and we hope you'll join us again for our next webinar. Thank you very much.